Alright, so hi everybody. In this new video, we're going to tackle something new which is related to multiple timescales. And in order to have a first approach to this beautiful theory, what we're going to study is the free response of a mass spring system, which is slightly damp with a small viscosity in a damper. Alright, so the mass spring system is a system represented like this. We have a mass, we have a spring over there, and we have a small viscous component here, which is there to dissipate some energy in the system. So the governing equation for this well-known mechanical problem is something that can be written like this: mass times acceleration plus viscosity times the velocity plus kq is equal to 0 if this is free of external applied load. Then we're going to consider two initial conditions, and the two initial conditions could be that displacement at the initial time is q0, something given, and initial velocity is equal to 0. So it means this is a free release problem, and the mass is just released at initial time t from initial condition q0. And the response is something, that looks like this. And we have dissipation until the displacement asymptotically goes to 0. All right. Then in this problem, first what we could do is to rewrite this in a dimensionless version, of course. And to do so, we know that we need to find first a characteristic time scale. All right, so first you start with the independent variable of the problem, which is time. All right, we have time t, and we're going to rewrite the time t as a characteristic time multiplied by a dimensionless time tau. And we have the unknowns of the problem, which might also need to be rescaled, and this can be done just by rewriting that the displacement q is a reference quantity multiplied by x. Okay, we can think of the different parameters we have in the problem to construct dimensionless characteristic time and characteristic displacement. That can be quite quick. Mass, this is in kilograms. Then we have c, the viscosity. This is in newtons seconds per meter. We have the stiffness K, which is in Newton per meters. And then we can also add probably the initial displacement Q0, which is in meters. The mass, let's just put it like this: Newton second square divided by meters, right? This is the same. This is a force divided by an acceleration. All right, so you see basically that with these three quantities, you see that newtons and meters, they come together. So there's no way to distinguish newtons and meters, especially if we forget about the viscosity, which is small. And of course, we should not use this to write the scaling. So there's no way to get a characteristic displacement based on that. And that makes sense, right? Because if you just look at the original governing equation here, you see this is a homogeneous linear equation. So you can multiply q by any quantity, and this is still valid, all right? So it just means that there's no way to get a characteristic displacement based on that. The only way to get a characteristic displacement is to use the initial condition, all right? So that's what we want to choose. And a characteristic time, now we should be used to that. So this is going to be a small quantity. So we're not going to use the viscosity to define a characteristic time. The only way to define a characteristic time is to use the mass and the stiffness. And so definitely, if you have already studied some problems in mechanical vibrations, so definitely we understand it should be something related to the natural period of the structure, or even better, the inverse of the circular natural frequency. All right, but to convince just ourselves about that, what we could do first is to divide the governing equation left and right by the mass. All right, so we're going to start from the governing equation here, divide by the mass, m. And so this is equivalent to solving 2 omega times the damping ratio xc, first derivative, omega squared times q is equal to 0. And omega is the square root of k over m. And this is the circular natural frequency. This is how it's defined. It's expressed in radians per second. All right. And so we could imagine, of course, as we played this game already several times, we could imagine that we don't know the characteristic time, and let's just see if it naturally comes out of the equations. And so it means that just by rewriting this with the characteristic time and characteristic unknown, we would have something like this: squared characteristic time times x, second derivative, plus twice omega xc, first derivative of q. All right, so we have a characteristic q over a characteristic time, plus omega squared times q, characteristic times x, and this is equal to 0. Okay, from this you see that, and this confirms what we said earlier, q star disappears, and then we can multiply left and right by t star squared. All right, so this means that we would obtain second derivative plus twice omega characteristic times xc, first derivative, omega squared t squared times x is equal to 0. We want to say that the viscous term is small, right? We said that the viscosity is something that is small. So we don't want to use this definitely to define the characteristic time. And so the option, which is left as the only option we have to define a characteristic time, is, for instance, to set this equal to 1. And this indeed corresponds to what I had written earlier here, that the characteristic time is the inverse of the circular natural frequency. All right, so this means that this is equal to 1. And then we want to say that what remains there, so twice times the damping ratio, okay, twice times the damping ratio, we want to say that this is the small quantity. And the damping ratio xc is already something that has no unit. So definitely we need to say that twice xc is a small number, or even better, because I would like to introduce a small parameter, epsilon, and to give it at the same time a physical meaning, right? So I'm just going to keep 2 in the governing equation like this, just to indicate that in fact the damping ratio xc is nothing but a small quantity epsilon. All right, so that's the equation we need to solve. It's being rewritten now. And what we want to do then is to transform also the initial conditions. Initial conditions are just over there. All right, position at initial time is q0. So if we divide this by, let me just rewrite it. That might be probably more clear. Means characteristic position times x at initial time is equal to q0, or in other words, x at initial time is q0 over q star. And let me just define this as equal to 1. Okay, I introduced this earlier just to make it simple and crisp. And then we have that the first derivative at initial time, which is nothing but this, is equal to 0. And we have that the first derivative of x is equal to 0. That's the second initial condition. All right, so that's the problem we want to solve. It has actually it has an analytical solution. This is a very simple linear differential equation. And so we can just have a glimpse at the exact solution to that problem. It is in fact x as a function of tau, which is the dimensionless time we have redefined, is the exponential of minus epsilon tau multiplied by the cos of tau square root 1 minus epsilon square plus epsilon over square root of 1 minus epsilon square times the sine of tau square root of 1 minus epsilon square. All right. This is not too difficult. This is probably a little bit complicated, but we see that when epsilon is a small number, there are a few things that probably can disappear, right? You see this epsilon here is such that the sign, which is between between -1 and 1, is multiplied by a small quantity, and probably this can be disregarded with respect to the cosine. And so I would expect that the solution is something that is approximately something that looks like a cosine, all right? And indeed, we do expect that the solution is a cosine which is modulated by a slowly decreasing exponential. So this would be exponential of minus epsilon tau, and starting from 1, and this multiplies a cosine, which is also something that starts from 1, and this is indeed what we do expect. This is x as a function of tau. All right, so we could start with a regular NZ, okay, just to see what our standard approaches would provide. And so if you want to plug in there a regular ansatz, what we would do is to say just x is x0 plus epsilon x1, and then small things, okay? And we could expect doing this. This is probably a little bit naive, but let's try. That we have a leading order solution plus a small perturbation, which could perhaps provide x1. We will see in a minute that this is definitely not the case, but it's definitely also worth trying this to convince ourselves that it will certainly not work. All right, so we need to substitute this into the governing equation and in the boundary conditions, all right? You remember that when we deal with differential equations, we need to substitute the ansatz in both the governing equation and the initial conditions. And so if we substitute this in the governing equation, what we have is second derivative of x0 plus epsilon x1. I'm going to drop epsilon squared terms just to keep it simple here, plus twice epsilon x0 first derivative plus x0 is equal to 0. And then initial conditions, we have this, and we have the first derivative. Epsilon x1 is equal to 0. All right, so at leading order, what we want to solve is second derivative of x0 plus x0 is equal to 0 with the initial condition at tau is equal to 0, that the position is equal to 0 and the velocity, position equal to 1 and velocity equal to 0. All right, quite easy. The solution of that equation is something that can be written a constant times a cosine of tau plus b constant times the sine of tau. All right, so if we look at the boundary or initial conditions, x0 when tau is equal to 0 is equal to a, right? Because the cosine is equal to 1 and sine is equal to 0, and it just tells us that this is equal to 1. And the first derivative, I think we can go quickly with this. So derivative of the cosine will provide minus sine, which vanishes. And what remains is b, and this one is equal to 0. All right, so we have x0 is nothing but the cosine of tau. Okay, not too bad. It just says that the initial condition, apparently the leading order solution is something that does not vanish. It is something that remains with a constant amplitude in time. I said not too bad, but not too good either, because what we are going to do here is to add a small perturbation to this, and the small perturbation definitely won't be able to capture the difference between what we had in the leading, which was oscillating like this, and what we do definitely expect in the actual solution. All right, so this is already just an example, a good indication to show that what we're doing here is certainly no good. All right, and the reason why this doesn't work is that the system is only slightly dissipative. All right, so we have a small dissipation in the problem. All right, we said that the damping ratio is something that is small. Damping ratio takes some time, okay, which is called to the memory of the system. It takes some time to be effective. And unfortunately, this long time or this slow time is something that we have not explicitly used in the regular ansatz. All right, so actually there's no way to capture the influence of the small damping in the solution we get at leading with this regular ansatz. The only thing we get in the unperturbed is something like this, and unfortunately in the unperturbed what we saw is that the oscillations remain continuously with the same amplitude. Okay, so no dissipation at all. So this is going to be bad, but though, let's just have a quick look at what the next order would provide. And the next order would provide, oops, I just realized here that I'm probably missing one term over there. Epsilon x1 is equal to 0. All right, so the second, or the first correction of the second order will be something like this. Second derivative of x1 plus x1 is equal to minus 2 first derivative of x0. And minus 2 times the first derivative of x0 is the derivative of cosine, so minus twice, so this is plus 2 sine of tau. All right, and so next, the solution to that equation will be another constant times the cosine, another constant times the sine, plus a particular solution. Let me just call it xp. We need to find the particular solution, and we need to be careful here that the right-hand side, here, sine of tau, is already a solution of the homogeneous problem, right? You see here, we do combine the two solutions of the homogeneous problem, and sine of tau is one of them. Okay, so it means that the particular solution, xp, actually can't be sine of tau, simply because sine of tau is a solution of the homogeneous problem. So if you want to replace sine of tau or anything like a constant multiplied by the sine of tau, if you want to replace this in the homogeneous problem, you see that the second derivative plus x1, they will vanish, and this will return 0, so there's no way to state that this is a particular solution. All right, so instead you probably remember that we use a technique which is called exponential polynomial combinations, combinations, and we're going to say that xp, the particular solution that we're looking at, is something like alpha tau cos tau, and possibly here we could also use beta tau times the sine of tau, okay, which is something I'm going to drop for now. Well, if we do that, you see that the first derivative of xp is alpha multiplied by cos tau minus alpha tau times the sine of tau. And that's for the first derivative. And the second derivative of xp, we need to differentiate this once more. So we have minus derivative of alpha cos tau and derivative of this. So we have minus alpha times the sine of tau. Then once more, so we have minus twice alpha times the sine of tau. and then minus alpha multiplied by tau and the cosine of tau. All right, so that when we add xp and xp double prime, we see that this and that, they do disappear. All right, they cancel each other. All right, so we end up with minus 2 alpha sine tau, and we want this to be equal to the actual right-hand side. All right, so this should be equal to 2 sine tau, meaning that the alpha we need to choose is equal to minus 1. All right, so it means that the particular solution is nothing but minus 1 tau cos tau, and so x1 is c cos tau plus d sine of tau minus, so this is alpha, tau cos tau. And so we see that the total solution that we would have, all right, which is asymptotic, at least this is what we think, to x0 plus epsilon x1 is cos tau plus epsilon, a small number, times c cos tau. Oh, we should use the initial conditions to determine c and d, but that's not something I want to do just right now. I would just like to observe what we're going to have there. And what we do observe is that at leading we have the cosine of tau, and then in the corrections we have a small number plus tau cos tau. And so it means that at leading we have something that is, oops, like this, all right, and so on. And then for the first correction, we have something which is much smaller, because this is epsilon times cosine and sine. But we see that this is multiplied by tau, meaning that this in fact has the same period, but it grows with time. So I'm just going to represent this a little bit exaggerated here, but you see that the amplitude is supposed to grow with time. It should be tangent to this line, of course. Okay, this sketch is not perfect, but you just get what I mean. And so it means that after a certain time, when epsilon tau has order of magnitude 1, we see that x1 has the same order of magnitude as x0. And this is very bad. And this is very bad because remember in the very beginning of perturbation techniques, what we had seen is that we assume that every other term in the sequence is much smaller than the previous one. This is what we meant by asymptoticness of the sequence. And so after a certain time, when tau is of order 1 over epsilon, after a certain time, unfortunately, we lose the asymptoticness of the sequence. And the solution, of course, is wrong. It doesn't work. All right, so it means that the solution we have here is fine, but at short time only, when tau is not too large. Is it interesting? Probably not so much, right? Because if you want to study a mass spring system like this, which is slightly damped, what you would like to see in the solution definitely is that the amplitude of the motion decreases after some time. And after how much time does it decrease? It decreases like a decreasing exponential, and after a time that is indeed quite long, because you need tau to span at least 1 order of magnitude, such that epsilon tau is not small, and the damping can enter into the picture. All right. In practice, we just translate this by the fact that we need several oscillations for the damping to be efficient and the energy to have efficiently vanished or dissipated in the problem. All right, so this is not good. This is not good at all. And this term actually has a name. It's qualified as a secular term. Okay, this term or this qualifier, secular, comes back to Lindstedt's work, certainly, who studied Lindstedt's works, who studied celestial mechanics and used regular ansatz first and realized that it doesn't work. And the problem, in his opinion or in his observation, were that the terms like these terms should disappear, they should vanish from his computations. Otherwise, they would, after a long time, which is of order 1 over epsilon, after a very long time, they would create problems in the asymptoticness of the sequence. And a long time for him in celestial mechanics was actually a few centuries, and this is why the term became a secular term. All right, so we need to do something else, and we definitely want to recognize that in this problem, there are two timescales. One fast, which corresponds to the fast oscillations, all right, which is the fast dynamic of the problem characterized by the timescale tau. And we have a slow dynamic in this problem, which is related to the decreasing envelope. And this time scale is governed by a slower time scale, epsilon times tau. All right, so we could, to make it clear, we could call these two times T1 and T2. And this is hinted also by the regular ansatz, right? We have seen in the regular ansatz epsilon tau. All right, so if you don't know how slow is the slow time, because it could be epsilon squared times tau, it is always a good idea to start with a regular ansatz. Just have a look at the solution you get, and you see when you start to lose asymptoticness. When you start to lose asymptoticness, it means that this is a slow time scale that you need to consider. All right, and so instead of searching for a solution that is written in the format x of tau, we're going to seek for a solution that is written as a combination of two time scales, T1 and T2, which are fast and slow time scales, right? So we could write y is a function of tau and epsilon tau. All right, but this is not what I want to write to start. I'm just gonna write, to make it super short, T1, T2, all right? And we want to understand that T1 and T2, both of them are functions of tau, all right? Meaning that if I want to compute now the derivative of x or any other quantity with respect to tau, let me just write x so this is clear. What we want to do, we apply the implicit differentiation theorem. So we need to compute a first derivative with respect to T1 of y. Okay, let me just drop the arguments, or I can keep the arguments. This is the first time we do it, probably. Then we need to differentiate T1 with respect to tau. And then we have the second partial differentiation with respect to T2, like this, multiplied by T2 by tau. And this, because T1 is equal to tau and T2 is equal to epsilon tau, this is equal to 1, and this is equal to epsilon. All right, so in short, we would write something like the derivative with respect to tau is a derivative with respect to T1 plus epsilon, a derivative with respect to T2. That's typically what you would see in standard scientific publications using multiple timescales approaches. And so the second derivative is this operator squared or applied to itself if you want. All right, like this. So this is the second derivative with respect to t1. Then we have a first cross derivative. In fact, we have it twice. And we have another derivative with respect to t2, which is also multiplied by epsilon square, like this. All right, so first what we do is to rewrite the governing equation and the boundary conditions with the new timescales. All right, so if we restart from the governing equation, we had, probably I should copy it over here so that we keep it with us. All right, so we have the second derivative with respect to time tau. So it's going to be second derivative with respect to t1 of y plus twice epsilon second derivative with respect to t1, t2. Let me just drop again the epsilon squared terms. It's going to be easier. So we have then plus twice epsilon times the first derivative of y, then plus y. This is equal to 0. And then we need the boundary conditions. So the first boundary condition will just say that y, when t1 and t2 are equal to 0, because this initial condition here means time tau is equal to 0. So this is equal to 1. And then we have the first derivative plus epsilon dt2 y that is equal to 0. All right. So once this is done, we use an ansatz. We use a regular ansatz. And then what we can say is that just by doing what we did here, and which is really the keystone or the key step in the process, we just said that instead of looking for just a single function of time tau, we're going to explicitly state that there are two different time scales in the problem. By doing this, we're going actually, or to, in fact, to expand a little bit. All right, so we are searching the solution in a space that is kind of larger or bigger than what we just should use. And so it means that there will be some freedom later that we can exploit in order to compensate the fact that we decided to expand at a certain time. All right, so I'm going to use a regular ansatz, then just as we usually do, just say that y is y0 plus epsilon y1 and so forth. So I'm going to rewrite the governing equation. Second derivative with t1 of y0 plus y0. I'm going to just also collect the different terms together. We then have epsilon second derivative with respect to t1 of y1 plus y1 plus twice cross derivative t1, t2, y0 plus twice t1, y0. And this is equal to 0 plus other epsilon square. That's the new governing equation, and the boundary conditions will just say that y0 plus epsilon y1 is equal to 1 at t1, t2 is equal to 0. And first derivative y0 plus epsilon times t1y1 plus t2y0. This is equal to 0. Same at t1, t2 equal to 0, 0. All right, so the leading is very similar to what we had earlier. And boundary conditions, y0 is equal to 1. And the first derivative is equal to 0. Then what we should do here is to solve those equations. What we get is something that is very similar to what we had before. So this is a constant times the cos of t1 plus a constant times the sine of t1. The only difference is that because we are dealing with partial differential equations, these are just constant with respect to t1, but they still remain functions of t2. All right, so initial condition, if we replace this expression for y0 over here, then what we see is that the sine vanishes, the cosine is equal to 1. So we have just that a when t2 is equal to 0 is 1. And if we do the same with the second boundary condition, initial condition, is that b when t2 is equal to 0 is equal to 0. So we can't actually determine the exact expression of a of t2 and b of t2, but we could only determine the value at the origin. They correspond to the slow dynamics, all right? They correspond to the slow time scale, that's what we said. And you can just figure it out as something that happens just over there, all right? So we're looking at the problem over the first few cycles. And what we say is that during the first few cycles, we're just able to capture what's going on at the original time, at the origin of time, and we're not able to capture what's going on later in time. All right, and to do this, let's go to the next order. If we go into the next order, then let me probably just rewrite the governing equation, which is this one. All right, we have it there. And this needs to be equal to 0 with initial conditions that are y, y1, 0, 0 is equal to 0. And first derivative with respect to t1 is equal to minus derivative of y0. Okay, so we have the same left-hand side, and then this is going to go to the right-hand side. So let me just write the right-hand side here is equal to, probably it's a good point to compute the partial derivative of y0 with respect to t1, which is in fact minus a. I'm going to drop the argument of a just to make it shorter. All right, but keep in mind this is a function of t2 minus a sine t1 plus b cos t1. All right, so if we push this to the right-hand side, then we have minus twice the derivative. So this means plus 2a sine t1 minus 2b cosine of t1. And then we need also to do the same with the same quantity, but differentiate it once with respect to t2. So this is going to be plus 2 first derivative of a and minus 2 first derivative of b. cos t1. Or we could rewrite them like this. Cos t1. All right, so here we are. And so the solution of the problem will be y1 is equal to another constant c2, which is a function of the slow time scale t2, cos t1 plus d times the sine of t1, and then a particular solution, which I can write yp. Then in the particular solutions, we need to have a look at the right-hand side, and we are facing something that is kind of similar to what we had before, because on the right-hand side, we have sine t and cosine t. Sine t definitely is going to require things that behave like t1 cos t1, all right, multiplied by some quantity. The other one is going to be something that behaves like t1 sine t1. Okay, I don't necessarily want to write them anymore because I know these terms will create definitely issues. And why will they create issues? Because of the polynomial exponential approach, I have to multiply these by polynomials, which definitely grow in time, multiplied by the cosine, and polynomial, which will grow in time, multiplied by the sine. And so because the sine and the cosine here are already solutions of the homogeneous problem, they will definitely create secular terms, solutions of the homogeneous problem. All right, so these will create terms that grow unbounded. And so we call them secular terms. All right, and these secular terms, we don't want them. So we're going to use our freedom at this stage, use our freedom to impose that the secular term do vanish. In this case, there's just two terms in the right-hand side. There might be more. There might be non-secular terms. All right, if it was the case, then we would have written here plus non-secular terms. All right, but in this exercise, there is none. All right, we just have two terms. Both of them are secular terms, and I want to get rid of them. Okay, so we're going to use our freedom to impose that the secular terms disappear. And so it just means that a plus first derivative of a is equal to 0, b plus first derivative of b is equal to 0. It means that a is a constant exponential of minus t2, b is a constant times exponential of minus t2. And we see that we have two first-order differential equations for a and b. And what is good is that you see earlier we couldn't determine those functions of time t2, but we had two initial conditions here and there, which are the two conditions we can use now in order to determine a0, b0. Okay, right away we see that a0 is equal to 1 and b0 is equal to 0, which means that b is consistently equal to 0 for any time t2, and a is the exponential of minus t2. Exponential of minus t2, which means that if we want to go back to the solution of the problem and say that x is asymptotic to y0, of course, in practice, there could be a plus an epsilon times y1 and so forth. But usually when we use timescale, we usually are already quite happy to get a picture of how things look like. And y0, if we come back to its definition here, y0, b vanishes, that's what we've seen, is equal to a of t2, which is exponential of minus t2. T2 we define this as as epsilon times tau, multiplied by the cosine of t1, and the cosine of t1 is the cosine of tau. And what we dropped is terms of order epsilon. And this, in fact, is nothing but what we were expecting. So we have the decreasing exponential that just modulates the cosine function. All right, so what does it work? It works because we explicitly stated that the solution of the problem happens on two different time scales. And if we had not done that, this is what we could observe at the very beginning with the regular ansatz, we would never have obtained something that would decrease in time. Instead, it would increase in time, and we would have terms that become increasingly important over time and over some centuries in the early works of Lingstedt, and this is why we call them secular. All right, so what we do in the multiple timescale method, we explicitly say that there are two timescales in the problem. We rewrite the governing equation first with the timescales that we have identified. Once this is done, so the entire problem is rewritten, so both governing equation and boundary conditions or initial conditions. Once this is done, we use a regular ansatz, put everything in the problem. We get, at leading order, the general form for the leading order solution. And then we get values for initial values at those constants of integration, which had become functions here. We can't determine them, but if we go to the next order, on the right-hand side, we see that there might be some secular terms. We need to identify them, and we use our freedom in order to impose that they disappear. This is going to provide two differential equations or some differential equations that you need to solve with the initial conditions that you get at the leading in order to get the full slow time evolution. All right, this is just a very quick picture of what multiple timescales look like. There will be another very short video coming in a few minutes where you will see how this is in practice implemented, and even with a few shortcuts to make it much faster and much more efficient.